Okay, thank you. Well, as you can see on this picture from Gary Larson, physicists, even the greatest, had to learn about economics. So now we are going to see if economics and mathematicians have to learn about something. Well, I'm going to talk about question of economic model and dynamical economic model in a finite world. I will go into something that Charles loves for decades now. And so we go. First, as Charles showed you, you can define as many models for economic as you want. At first, you can say, okay, nature gives us for free. So if it's free, I don't count it. If I don't count it, then it's perpetual motion. That's great. Why not? Okay. But if you are more realistic, then you can do like what Charles did. You say, okay, there is the classical economy, but we have to take care that we are in a real world where we've got energy going and energy going out from our system. There are different versions of this, and then you can see that Berg and Hall recently proposed another model which is almost the same. And here you've got the resource, and here you've got the waste, here you've got the energy, and here you've got heat. So we deal with this kind of things. Okay, now what's the problem? How can we build a model? First, does this model have to do something with physics? Does this model have to do something with mechanics or thermodynamics or whatever? So we are going to try to answer to a few questions. What do we learn from mechanics? I mean, in the economic area. What do we learn from equilibrium thermodynamics? What do we learn from out of equilibrium thermodynamics? So there's a lot of thermodynamics in my talk, so if you want to leave the room now, you can. Okay? So next, does economics have something to do with thermodynamics? That's the core of my talk. And then I will propose a model where a few things matter. I think there's some question of conservation, friction, and rate, because rate in an economic system, rate does matter too, as Howard Odum said. Okay, let's go back to the 19th century. And here's a paper from Léon Walras, the beginning the beginning of the last century, and he says, okay, economists and non-mathematicians call out, and even mathematicians refuse to accept that satisfaction could be measured. With the first, I mean with the economists, there's no use to discuss with them. Sorry. Them and us don't speak the same language. But with the mathematicians, it's different. We may explain something and maybe we will agree. So now, if you are economists, you go on the right side. If you are a mathematician, you go on the left side. And if I follow Walras, I should only talk to the right side. Okay. In fact, what says Walras? Walras says that economics has really to do with mechanics. Why? Because at that time, mechanics, rational mechanics, I mean Lagrangian, Hamiltonians, and so, were the king of the physics. So it was absolutely natural to consider, okay, let's try to put our physics into this new area. Okay. And then he described things using the Lagrange approach with the minimization and optimization of the satisfaction. Okay, why not? But at the same time, another guy from the same school, Polytechnique, whose name is Hermann Laurent, wrote to Léon Walras, asking him a few things, and in particular, I'm sorry, Professor Walras, please let me know, is your approach integrable? Is your approach integrable? That means, does your functions are state functions or not? Or in other words, what you optimize locally, really locally, can it be extended or not? And they exchanged many letters, and at the end, Walras told to Hermann Laurent, please ask Pareto, and Pareto did the same. You can read the story in the More Heat and Light book from Philip Mirowski. Okay, then another guy, a chemist, Frédéric Soddy, said, okay, no, in fact, economics is really thermodynamics. Okay, the laws of thermodynamics that express the relation between matter and energy govern the rise and fall of political systems. So, well, job is done. And later, Paul Samuelson remind a talk he had with Wilson. And Wilson was a student of Willard Gibbs himself. And Wilson told to Samuelson, probably you should consider the Gibbs equation number 133. And from this equation, 133, you may find something interesting. And then 9 years later, Paul Samuelson did, badly. And he did using the Le Chatelier principle, but he missed the correct use of the Le Chatelier principle. Okay. And later, Samuelson finally said that economics has more or less nothing to do with thermodynamics. Okay. That's
they don't even operate.
Sorry?
They don't even operate, he says, in economics.
Yeah. So at that time, we may say that this is a mess. Okay. So what is equilibrium thermodynamics? I use here what we call the Callen approach. Okay. We consider that there is something which is an extensive function that here we call entropy, which is a function of extensive variables. So it can be the energy, the volume, the number of molecules, everything extensive. And extensive means that if you've got a certain amount of the thing and you cut it in two parts, if this is 1, if I cut it in 2, then I've got half and half. This is 1 liter, I cut it, I've got 1/2 of liter, 1/2 of liter. If it is intensive, this water is at 300K. If I cut in 2 pieces, I don't have 150, 150K. They have the same temperatures. So that's the difference between intensive and extensive. Okay? And then what you are going to do is to try to get a principle. So principle of maximum entropy, for example, and you derive the equations. So some kind of equation that let be an extensive function of state. Let y here, so it's extensive, the variables are extensive, and you add constraints. Constraints in thermodynamics can be state equations and other constraints of the boundary conditions and so. And then you want to minimize the things, so you build the Lagrangian of the system, where you see that these equations are 0, so you can say that I take y and I had something which is 0, and I will do the minimization on all the variables. And then I've got new variables here, which has the partial derivatives of my functions. And these variables are intensive variables. Okay. So there are intensive quantities, and we may have some relations between intensive and extensive quantities, which may be the state function. For example, for the perfect case, PV is equal to RT and N RT. This is an equation where you've got intensive and extensive variables connected by a given law. Okay, so in thermodynamics, what you do, you take y is now the entropy, okay, function of extensive variables, right? These extensive variables are well known. It can be the volume, the number of molecules, the internal energy, whatever you want. I've got some constraints, which are the equations of state and initial and boundary conditions. So there are a certain amount of equation here. You do your Lagrangian, and then you get the potentials. What are the potentials? If you have done a few thermodynamics, that you will find the following potential: 1 over t, p over t, minus mu over t, which is mu is the chemical potential. Well, then, what you can say? You can say that you've got an expression which is the Gibbs expression. That means that the derivative of the differential of the entropy is given by the term, the extensive terms. You should add the internal terms, but the sum of them are 0. This is the Gibbs-GM equation. And then from there, since you've got the correct structure of the thermodynamics, then these partial derivatives here allows you to build what we call the fundamental equation of the system. And then when you have that, you've got what we can call a thermodynamic structure. I mean, sorry.
Any questions?
Okay, great. Well, it's the first time I speak thermodynamics and people are laughing so much. That's a very good news for me. Okay, and here you really have the structure of the thermodynamics. You've got the fundamental equation, and you've got, of course, the equation of state here, the equation of state, for example, of a perfect case. Okay? Now, let's do the job with economics. Let us say the y function, extensive function, is now the utility. Utility is a function of also extensive variables, which are the goods that you want to purchase. Okay? And you've got price density. I mean, price density is euro per liter or euro per unit of mass or whatever. So it's intensive. Okay? So we've got the correct structure until now. And here are the partial derivatives, which are the marginal utilities. Right. Things are going really well. Great. So there is a first question. Okay, do you have the state equations of your system? Do you have the state equation as the equation of the perfect case? In an economic system, do you have all the equations that links the internal and external parameters? I don't have the answer. That's a question for me. Do you have external constraint? Maybe. Okay. So you imagine that, okay, that's not a problem for the moment. I do the calculation of my Lagrangian. I do the optimization. I calculate my derivatives. And I obtain that we know in economics, which is the prices density, and here the marginal utilities. Okay, everything is good.
You're saying that the constraints are there, but you don't know them.
I don't, for me, now I imagine that there may be this constraint and there may be state equations. I will go back to this question later. But at the moment, okay, I say, well, it's not my problem now, so I go back and then I build the Gibbs expression and then the Euler expression. Well, but there is a question which is in fact the same as you mentioned. Do marginal utilities can have the same statute as potentials? That's the question of integrability. I mean, this, of course, has a meaning locally. This is not a problem. But is it integrable? I mean, do we have the statute of thermodynamics? And that's a huge question. But there's more. With this mathematics, when you have something interesting, then you go further. So let's say, well, when I do thermodynamics, at first I hate it, and after I love it. Okay? So I say, okay, I want to calculate the thermoelastic coefficient. I want to know how much increase of pressure I will get if I increase the temperature. Okay? How much will I increase the temperature when I put some heat into, which is the specific heats. And I can do that at constant pressure, or constant volumes, whatever. Okay, these are things you may have learned at school, or at college, probably. Well, can we say anything similar in economics? The answer is yes. But yes, maybe not a good news. Anyway, this is yes because if you use exactly the same formal approach, exactly the same approach, then you will build these kind of expressions. And what are these kind of expressions? These are the famous elasticities. And then there is another question. What's the question? So, there is an economic material. I mean, there is something I can study and say, if I change the amount of money, then the economic pressure will change, and so and so and so. I've got the elastic coefficients. But it's still a question for me, because if you want to say that, that means that there is a real material with specific and intrinsic properties. And on this material, you can do things. But this material has to be defined. And defined by what? By state equations. If you don't have the state equation of a perfect case, then you cannot say anything about the amount of increase of pressure when you change the temperature. Okay? And the point is here. Okay? If the state equations are known, okay, PV radial equal nRT. So does the fundamental equation. Then it becomes integrable. And Hermann Laurent, still there, is happy. But, and then you've got integrability, Maxwell relation, and then you've got the Le Chatelier-Braun theorem. Le Chatelier-Braun, why? Because Le Chatelier, just when you consider one intensive parameter, you increase locally the temperature, then you've got locally a strong gradient of the temperature, and you reduce this gradient on the temperature. But if P and T are connected, then you increase the temperature, locally you increase the pressure, and it's the action of the pressure, which is the second potential, that gives you the decrease of the temperature and the decrease of the potential. So Le Chatelier-Braun is an extension of the Le Chatelier principle through connected intensive parameters. But again, that means that underlying there is state equation. Okay. Is there an economic material? Not sure. Yeah?
I'm not quite sure this is applicable, but you know the work of Mirowski, right?
Yeah.
And he said he borrowed the equations from physics, but used them completely wrong. I mean, back in the
Yes, there is, with Paul Samuelson, there is two problems. Maybe more, but let us consider that there is two problems. First, there is this problem. If you want to use the Le Chatelier principle, then that means that you know that there are some state equations, first. And second, if you want to use properly the Le Chatelier principle, then you have to deal only with intensive parameters. Temperature, or temperature connected to pressure. The problem with Samuelson is that he made a calculation mixing intensive and extensive parameters. And then the calculation is wrong.
I'm trying to think of the word in physics, Hamiltonians.
Ooh, yeah.
And that Mirowski said that was the basis of the first such equations in economics, and where Hamiltonians in fact are based on conservation of energy, the way the economists use it violated the laws of thermodynamics.
Yes, but the question of the Hamiltonian is a question of variational principle. I mean that if you've got a principle of that says that the entropy for isolated system will go to its maximum, then in fact you build a variational principle. Okay? And the question is that, do you have the legitimacy to build a variational principle in something where you don't really know what is the material? Okay? Yeah?
Question about that. You can have a material and no equation of state. These are two separate things.
Yeah.
Equation of state means that the state, I mean, the value of the function depends on the value of some macroscopic parameter now, right now.
Yeah.
But it depends on the history of the thing. There's no equation of state.
Yeah. Yeah.
So
that means that the specific heat of the air is the same now and a few years ago. Yeah, sure.
So
and that's also the...
that material doesn't go necessarily with the fact that you have an equation of state. That's what...
You're right, but here the underlying idea is that you are supposed to have a material well known. You can imagine that there is a variation of the property of a time. That's not a problem. Then you have to stay, and it's always the problem in thermodynamics, you have to stay under quasi-static conditions. I mean, the macroscopic time variation are much, much, much smaller, larger than the microscopic one. Then you are okay. Okay? So there's a partial conclusion here. In fact, economics does not have the complete structure of thermodynamics. I mean, you can do local optimization, but there is no the complete structure. There is no problem with doing local optimization, absolutely no problem, until you don't claim it's general. So general, you should avoid that. There is no fundamental equation for the economy, nor variational principle, hopefully, because if I fall in love, and many people fall in love, and they change the amount of goods, and so, and so, and so, if this is really written in equation, that's not really a good news. That's my opinion. However, there's no ergodicity. That means that what we call the commissaire-priseur, that says, hey, guys, you all know the price of the goods and the number of goods, so now you go and we get to the equilibrium. That means that everybody knows the market, okay? In physics, in some way that says that the system is going to explore everything and then make the choice. But there's no ergodicity. Okay, so not general, and economic systems are not equilibrium systems. So the theory of general economy is not general. The theory of general equilibrium economy is not general, nor in equilibrium. Well, now what can we do? Then we go back to Joseph Schumpeter, because Joseph Schumpeter considers things not at equilibrium, but says that there is what we say destruction and creation. And this is really interesting for a physicist to read Joseph Schumpeter. Why? Because he says that there's friction in this. Why is it important for a physicist to get a friction? That means that when you've got a motion, you may obtain a steady state. If not, then you may accelerate continuously. But that's good news to have friction, because you can imagine that you may have some steady states first. And it's also very interesting to look to Joseph Schumpeter. Why? Because he says that there are, okay, steady states, so time does matter. And for a physicist, okay, that looks like Onsager approach. And also he said that there are also bifurcations. I mean, sometimes the innovation will drive the system completely and another branch. Okay, so that's the first part of the text here is more or less Onsager, and the second part is more or less Prigogine. So if we are with Prigogine, then we are in the world of the far out of equilibrium system where you've got structure. This is a picture from one book of Nicolas Georgescu-Roegen. He said that the neoclassic economy is just you use the resource and you put them in the sink, and at the end everybody's died. And he says, no, this is not the point. The fact is that our economy, are really cycles, dynamical cycles, very, very far out of equilibrium, like Rayleigh-Bénard rolls in the water when you hit the water. What do we learn from that? We learn that this structure is really stable. I mean, much more than a pendulum, a classical pendulum. Because if you have a pendulum using just classical mechanics, if you just put a perturbation, then you've got a precession. And it's a completely different story. Now, if you've got the Rayleigh-Bénard rolls, and you move the water, you destroy all the rolls. You wait, and then the rolls goes. So it's a good news. This is a robust structure, hopefully. Okay, but the bad news is that to maintain this very far out of equilibrium, you need a huge flux of energy. You need a huge flux of matter. If you don't have the huge flux of energy and the huge flux of matter, then you don't have any role anymore. Okay, I have to say a few words about the famous or infamous, if I use the words of Mayumi, who was a student of Roegen, fourth law of thermodynamics. We have to stop with this question of fourth law of thermodynamics used by Roegen, saying that matter matters too. Of course, matter matters too. And there's a dispersion of the element, and we have talked about that during the week, but please don't consider this is entropy in the thermodynamic meaning. Entropy, strictly speaking, is something which is an extensive quantity conjugated with what we call the temperature. and the product between the entropy and the temperature as the dimension of an energy. I don't mean that there are not questions of dispersion and statistical approach of the dispersion of the material. Of course not. But you may use the word you want, but please don't call it entropy. I think it's misleading for all the community. Confusing, yeah. Anyway, that does not mean that you have to put every thermodynamic analogies into the trash. No, you can use some categories from the thermodynamic. And I will show you that that's what we are doing. For example, here, just in the financial area, Yakovenko recently said, okay, I will build a monetary temperature. So I've got a certain amount of money, I've got a certain number of agents, which is the summation of all the agents, and the money is spread over all the agents. And then I took that, I optimized the system with a certain law. So I said, okay, everyone has 100 euro and exchange 1 euro when you meet someone. And if you do that, you obtain Gibbs law. Well, if you do the same, but you say, wait, well, I exchange some money, I exchange a fraction of what I've got, then you put an asymmetry in the relation, and you've got another kind of expression, okay? I have absolutely no problem with this monetary temperature. Just one thing. This is just the average of the amount of money. So you should better call it the average amount of money that each agent carry, okay? Why? Because if you use that, and you know that this is some kind of, it's a Canada Dry temperature, okay? But one day, a guy will say, okay, if there is a temperature, there's an entropy. If there is an entropy, then I can build an expression of a free energy, and then you are going into bad thermodynamics that do not serve nor economics nor thermodynamics. So some categories of thermodynamics can be used, but economy don't have the structure, the fundamental structure of thermodynamics. Anyway, this is interesting to see that if you use here the cumulative percent of people, the total net capital of wealth in pounds in United Kingdom 20 years ago. Well, the Boltzmann-Gibbs law here about equilibrium fits pretty well. Okay, let's go to fraction 2 or 3% of the population. And then this does not follow the same law. This is a power law. That means that it's exactly the same kind of shape we have when you consider plasma. You've got massive carriers in equilibrium, and some of them are very out of equilibrium. So now, the next time you will meet one of these 3% guys who are very rich, you can ask them, well, sorry, sir, did you notice that you were really out of equilibrium? Okay? But please, don't rebuild any thermodynamics from that. Okay, now I use a title used by Glusina and Mayumi a few years ago about this kind of analogy between economics and thermodynamics. And they are well literate. I show you some, and burned bridges. And even recently, we have some people that said, okay, we have to put the axiomatic foundation of the economics into. Well, but people take care. Here, he says, nor are there any available topological invariants on which to base a purely formal statistical mechanic. That's more or less what I said. Here, Wallace says, okay, if economics is to be considered as a science-based discipline, the principle of the physical science, including the laws of thermodynamics, must be appropriately applied. If, and here, a very recent sentence from Kummel says, we need to begin to incorporate energy and entropy thinking. Energy and entropy thinking, it's okay for me. But entropy thinking, but please, at the end, don't call it entropy. You can imagine the dispersion of the material. Okay. Well, now we can use the thermodynamics. We can use the fact that we have conservative laws. That means that we cannot substitute what we want in any way. Non-conservation of some physical quantities, utility is not, and money is not. Different between extensive and intensive. Intensive physical parameters quantities are interesting because they give you potentials. From there, you can derive forces and imagine out of equilibrium system. And intensive physical quantities are potential that gives you the possibility to measure the quality So you can get the access of the quality without mentioning entropy. People usually don't know that, but it's very important. You have to abandon the full thermodynamic parable, and time does matter, but there is no variational principle in out of equilibrium thermodynamics. Okay, anyway, here a tribute to Howard Odum, and a courtesy from Charles, who gave me a few pictures here, and Howard Odum took the assumption of Lotka. Lotka said that there is maximum principle, no maximum power principle. So system, biologic system, ecologic system runs at the maximum power principle. We go into detail in that, but yes, that's right. That's when Charles used and cut his wood, that the fact that if you use the chain with a very small pressure, then you get not a very good efficiency. If you use a very large pressure, then you block the chain and you've got nothing. And if you adjust properly, you are close to the maximum power efficiency, and then you do the job in a better way. Okay, but to do that and to think about that, you have to go at the good place, and you have to think. So here we change the ratio of, I don't know the word, the vitesse, the ratio of on your bicycle. Okay, the gear ratio in order to optimize your working point. That's good. And for all these things, you have to think, and Charles told me that this is the place where he thinks about science. Okay? And at the end, the point is, okay, here you've got trees, and you've got dead trees, so all the system works, and you've got some kind of heroes. I mean, you cannot have always living trees. And that...
Let me explain that just for one second.
I've got... just after, please. Just... Okay. Howard Odum used this maximum principle using a mechanical approach, saying that it's like a lift. You've got a weight here and a weight there. This one is larger than this one, and you say, okay, I can optimize the efficiency. So this weight is very close to this one. The process will be very slow, or I can use a very large one. So the process will be very fast. But if I do that, then this one will hit this part with a large kinetic energy, so this part of the energy will be lost. That means something very interesting, that you don't need to use thermodynamics to define an efficiency. The efficiency is just the ratio between what you recover divided by what you put in. And you've got this kind of curves. And Charles published 20 years ago a book about these questions. It's very interesting to see that Odum and Pinkerton did that in 1955, because in 1955 too, another guy, Jacques Yvon and Pierre Chambadal, here, he did the same job almost, considering the Saclay reactor, so considering nuclear power. So this is thermodynamics. And what he did, if you take this Carnot engine, this is a very nice Carnot engine, because you will recover the maximum power, the maximum work. But this is reversible, so it will cost you an infinite time. So if you derive the work by the duration, then you get zero power. Okay, so you have to deal with finite type thermodynamics, and what you do is under reversible engine. This is reversible, this is not reversible, and when you do that, and you get this expression, and this expression gives you a maximum, the efficiency at maximal power, which is close to half the efficiency, the Carnot efficiency. Though the story is almost the same, except that here you've got a parameter, which is the intensity. I mean the rate you are using, you are dealing with your process. So here, efficiency of power. So if we derive this, we have done it for 1 decade now, you can plot the picture of the efficiency versus power. If you've got an under-reversible engine then, but if you've got internal frictions larger, then you've got different shapes. And here with low friction, you can see that the maximum power and maximum efficiency are not the same points. So this is really interesting. Why? Because you can imagine that you've got some friction, you increase the friction, that you reduce here. You can imagine that you've got a fraction of your resource that is lost through time, then there's a leak, friction plus leak, and you can imagine that you've got the restriction access to this due to this term, okay, and the restriction access reduce, and if you put everything, that you may have something very, very small. Okay. So what we did now, we take the same picture as Charles showed you with the resource and the sink. So here the resource for one quantity and the sink, and we use the same approach. And okay, this is Canada Dry thermodynamics. I mean, this is like a thermal engine I mean, a generator. This is like a heat pump, but they are not really. And this is our Lego brick. So if we go into, we see that this is a resource, this is a sink. There is a natural fraction of recycling. Here, this is the production, which is driven by the intensity. If you increase the intensity, then you go from there. So at the beginning, you increase the power and the efficiency. So this is the safe region. If you increase, then you go to the maximal efficiency point. If you increase again the intensity on your system, then you go, you increase the pressure of the chain when you cut your wood, then you are at maximum power, and then if you increase more, then you go to have less power and less efficiency. At the end, you can burn all the fuel without doing anything. Okay? So we've got a parameter in our model, which is just m. If m is really large, larger than 1, you are in the safe region. We can calculate the value of m for maximum efficiency. If m equals 1, we are at maximum power, and here we are in an unsafe region. So this is for the production and how we consider things. This is the production. This is the demand, which is linked to a Leontief matrix. The Leontief matrix makes the connection between this sheet for one sector with other sectors. And this is the recycling, the forced recycling zone with a Leontief also. But this is a Leontief approach for the recycling zone. And then you can do the recycling of the thing. So when you take all the bricks, the number of you want, you can build a market with just material, energy, capital, labor. So at the beginning, just small matrix. But if you want to add many, many bricks, you can do. This is a toy model. This is not a joke. A toy model is not a game. A toy model is just a model that at first gives you a coarse description, not a fine description. Anyway, you've got the tendencies correctly. If you want to refine the model, you just have to add sheets. But every step you do, you control what you are doing. It is not a gas plant, okay? So this is really important for us. Now, what is really important too is that you can say, okay, my whole economy is driven by a given rate, which is the intensity, and this is the same intensity for all them. Yes, it's okay. Thank you. Same intensity for them. Okay. Then every sheet is driven by a forced intensity. As you can see here, the sheet just receives information for the production and the recycling. Here, there's a conservation of the matter, conservation of the energy. These laws are correct. But now, since they are connected through the same intensity, that means that some of the sheets may be at different values of the m parameter. Imagine that for this kind of matter, okay, we are in the safe region. So you may say that you can increase the intensity in the extraction of the wood because you are in the safe region. It's no problem. But imagine, oh, this is aluminum. We are yet at the maximum extraction of aluminum. If you increase the intensity by the market, for example, then you are going into trouble. Okay? And here, for the capital, you have debt. You are already in trouble. So you can have a panel where the different sectors, and when you change the intensity of the overall economy, you can see the different zone moving. Okay? And just every sheet gives you a flag with a scalar, which is the m value. My m is 100. You are safe. Okay. Just a smell test on one sheet. Okay. These are the potential. So the level of the resource, the level of the waste. Okay. This is the production, and this is the demand. The demand is in blue, and the production is in green. Here, the law is that the production tries to follow the demand. Not so stupid. What you can see is that here there are strong increase of the production, and then we reach the demand as everything's okay. This is the value of the m. At the beginning, you are in the safe region. You go back, and you never reach. Here it would be 0 if it was m equal 1. So you are always safe, and you always produce. There's no problem. Here you look to the efficiency of your production part. You got an efficiency close to half, which is close to the maximum power. That's not problem, but you are not exactly at maximum power because you are not at 0 here. This is the COP, the coefficient performance of the pump of the recycling zone, and you are in safe region also. If you look to the flux for the recycling, This is the natural recycling, which is more saturated, and this is the value of the forced recycling induced by the demand through the Leontief, the second Leontief matrix. Now you say, okay, my demand is here 1. I increase my demand by 15%. So you see that here the top is 1, here the top is a little bit higher. What do you see then? Same story, you begin in story, and your system is going to take a large amount of resource. Then you've got an increased amount of waste. And here in terms of M value, you have to see that the system is going down and it goes to 0, which means that here he is at maximum power. Is it sufficient? Let's see. Okay, at the beginning, things are correct. I follow the demand. But since the resource is decreasing, then this is shrinking. And then I lost, and then it breaks down. It's not 0. The things are doing what they can, but they cannot do the best. Then, what to do? You can see that here, there's a saturation of the recycling zone. Here, there was not. So the point is that we may change something and ask larger demand of recycling. Why not? Let's do that. And then it's the same story, same demand as before, but I increase here by 9% the demand of recycling. What I get here is there's no more shrink. Okay? There's still a difference of potential, lower than the first one, anyway. These are the fluxes, incoming fluxes. And this is the production, then now I reach the demand, and there's no problem. Okay, and what I can see here, that my M goes down close, not so close to 0, so I never reach the maximum power. I am always in the safe region, okay? And when we look to the recycling, we see that there's no more saturation. Okay, there's no need to use stock. Stock is always 0. In some scenarios, sometimes the fraction of the production goes into stock and then is destocked into the production. And here you've got the efficiency, close to half. And here the coefficient of performance of the recycling zone. Okay. So at the end, what can we say? Well, economics does not have the structure of thermodynamics. I have to say that again. There is no economical entropy, but quantity and quality approaches are possible. I showed you. There is no fundamental equation for the economy. Hopefully, there is no ergodicity. Economic systems are not equilibrium system. This is exactly not an equilibrium system under equilibrium, okay? But there is no problem with doing local optimization until we don't claim it's general, conservation laws, everything I said. I think I have to switch off now, and I want to thank you. Thank you.